Yeah. Okay. Hi guys. Welcome to Avionics Lesson 5 and Electronics. Yes. Okay. Today we are gonna learn about microcontrollers. Yay! Basics of microcontrollers. I'll be covering quite a lot of things. This is kind of outdated, but yes, let's move forward. Yes, microcontrollers. So majority of the course we've been dealing with a magic box called the ESP32. So now let's tackle what the ESP32 does. And so ESP32 is a microcontroller. It's essentially a tiny computer but packed into a small chip. So it's like your Intel CPU, your AMD CPU, but like smaller, less powerful, and more closer to your hardware. It's able to control hardware like literally at the barebone. So the difference between microcontrollers and CPUs, right, like your Intel chips and whatnot, is that microcontrollers are specifically tuned to control hardware, while computers like your desktop PCs, they are just communicating over network, not really doing anything to hardware other than a screen, computer, screen, mouse, and screen, mouse, and what's the one? Keyboard. Yeah, USB. And that's very high level. We are not tackling that. Yes. Okay. Yeah. Basically, that's what I said. And so microcontrollers can apply voltages to its output pins, and it can also sense voltages. So like think of think of a brain. Like a brain is your CPU, right? Then like your sensors is your 5 sensors. That is basically your microcontroller pins essentially. Yeah. So in electronics, signals are typically arranged from, let's say, 0 to 5 volts or 0 to 3.3 volts. And this is analog waveform, but analog is scary, and we're not tackling that in this course. And analog waveforms are hard to interpret with a microcontroller because of noise, and again to like sampling rate and whatnot. We are not tackling that.
Okay, so noise is basically like okay, remember how we had like capacitive and inductive coupling, right? So like basically you can have 50 and 60 hertz power in the walls. You can have random radiator power from like who knows where, and all of this can induce voltages in your circuit and create random currents. So this means that even if you apply an exact 3 volts to this line, that line can fluctuate a little bit or a lot depending on your environment. So this is electrical noise, and this is a problem for all the electrical circuits.
So RF, everything just affects the circuit, and we don't like that. Okay. So yeah, so we work with logic levels from typically 2 states. There are some crazy systems that use 3 states. Those are like Russian systems. We don't care about them. Yeah. So typically high or low, and low is normally represented by ground or 0 volts, and high is represented by 3 volts, 3.3 volts or 5 volts. Yeah, and so typically we define a range for like high, logic level high, usually 2.7 to 5. It depends on the chip, depends on like what type, whether you're using CMOS, whether you're using LV MOS, whatever MOS. Yeah, and low is from 0 to 0.7. This is because of noise. Yeah, so we work with 2 voltages, and this is you can see this is like can be interpreted as data,
Okay,
like
second.
binary.
Did everyone understand why we're using binary? Okay, so instead of like setting something to an exact voltage and then the exact voltage means something, I set it to either high or low, right? And then like that represents like a yes or a no basically, and because of math that like nobody really needs to know, like you can basically do any logic with just yes and no's. Okay, so
Correct.
like for example, I can set this to high, and then like does it need to be exactly 5 volts? No, can be like 3 point whatever or whatever. Okay, as long as it's above the minimum, then it's considered a high. And like for if I want to set it to a low, it doesn't have to be exactly zero. No need, you know. Like I said, like it can, as long as it's below 0.7 volts or whatever the minimum is, it's gonna work. Okay, so
Yeah.
this gives us a very strong like noise rejection, where like the noise has to be huge enough to like flip the state of it, which is
Yeah.
very difficult. Yeah.
So this can be interpreted as 1, this can be interpreted as 0. You can do it the other way, but no one does that. Yeah, so this is a specific encoding actually, which is non-return to 0, but there is additional information you don't need to know. Okay. Yes.
What's it called?
Non-return to 0. Yeah. So yeah, we typically work with 3.3 volts on like ESP32s and 5 volts on like your Arduino Unos, pick it. Yeah, basically all the old microcontrollers use 5 volts. Nowadays we use 3.3 volts on all modern chips use 3.3 volts. So let's stick to 3.3 volts. Yeah. So always remember this, never connect a 5 volt output directly to a 3.3 volt output. Why? Is because the GPIO port will get damaged and you'll find like that port stops working, maybe your microcontroller stops working, and like in general that's a really bad idea. So this is something you should look out for when you're designing a circuit. Yeah. And typically how you let's say you got a 5 volt input or output. Wait, let's say you have a 5 volt sensor that outputs 5 volt data. So you can use a logic level shifter, there are some chips for that, or you can use a simple voltage divider if you want to.
So a logic level shifter is a magic chip, and you put in a signal, a binary signal, and it goes from 0 to 5 volts, right? Then out comes the exact same signal, but 0 to 3.3 volts. That's it.
Yes.
And like this works for any logic levels. So 3.3 volt is the most common. There's actually 1.8 volt logic level as well for like even lower power things. Very good. I am annoyed that I have to use it sometimes. And then you have to use logic level shifter. So anytime you have like different chips or different microcontrollers on your circuit which have to talk to each other with different signals,
Yep.
levels, then put logic level shifter basically.
Yep.
Yeah.
Yeah, essentially that's the easiest way lah. Yeah. Okay, so GPIO, which stands for General Purpose Input Output. Why they exist is because it is the main way microcontrollers interact with the real world. And typically you control things like LEDs, probably
Okay, so this is why we call them pins, okay? Because everyone likes breadboards, you know. Breadboards are cool. We can like do things with the breadboard, and then like so you just plug the microcontroller board directly into the breadboard, and you do that with the pins, right? So even for like microcontrollers that are no longer designed for a breadboard, this is an ESP32 module. It's just got like these copper pads at the side. We still call them pins as a like historical reason. People understand what it means.
Yeah.
Okay, but so like this is pins, this is pins, this is pins. It's the same thing. Yeah.
Yeah, so yeah, that's why we call them pins. And okay, so GPIO, they allow us to connect LEDs, they allow us to connect motors, and you actually can, even though it's digital, you actually can change the brightness of LEDs using a magical thing called PWM, which I'll discuss later. Yeah, you can do a bunch of stuff with it. You can even measure voltages. Yeah, so I'll be talking about output types first. So GPIO output means the microcontroller is doing things in the world. So like you want to turn on an LED for instance, or you want to spin a motor, a servo, or a relay, and typically it's on or off. Okay, so we are dealing with on or off, or a PWM signal, which I'll explain later. Yeah, so there are two types of GPIO output, which is push pull and open drain, also called open collector. So push pull is basically push pull is used when you require a higher current drain. So okay, so let me explain. So this is our output pin. This can either go high or low. right? So when it goes high, this transistor would turn on and this transistor would turn off. So when this transistor is on, what happens? Current will flow through here, and because this has a small resistance, the voltage across this will be small. So that means this output will be put high.
The output will basically be VDD, which
Yes,
is 5 volts.
basically
Okay.
VDD, basically 3.3 volts. Yeah, and same thing here. The NMOS is turned off.
And on,
And
right?
yes, turn on, and the PMOS is turned off. That allows the output pin to go low. So in this case, it is either transistors can be on, but not both. Okay, so the microcontroller will control these transistors in such a way that only one of them must be on at a certain time. There is also a special state where both of them are off, which is called high impedance, but we won't discuss that. Yeah, so it either can go low or high. Yeah, so yeah, the reason why it's called push-pull is the current gets pushed through the output pin, and during the pull phase, when it's pulled down, the current gets pulled. So that's the reason why they call push-pull. Okay, so the next type of output is an open collector.
Did everyone understand push-pull? Cool. If we have time, we will explain why this justifies the capacitor. If we have time, you can.
Okay, justifies the capacitor. Yes, yeah, we have time. Yes. Okay. Yeah, so this is how an open collector. In this case, there are two different types of transistors here. We covered MOSFETs, but we didn't really cover BJTs. BJTs are current controlled, so like current will flow through here, and a massive amount of current will flow through here. So usually, we call it the pin of a BJT. This is called the collector. So that's why this is called open collector, and this pin of the MOSFET is called the drain. So that's why we call it open drain. So it's out in the open. Yeah, and typically this is useful when we have later I'll show you, but typically this is useful when you want to connect multiple outputs in parallel.
So this kind of GPIO, it cannot set the pin to high
at all.
It can only set it to low.
It can only pull it to ground.
Yes. So the difference between MOSFET and BJT, MOSFET is a voltage controlled device, which means that the more voltage I apply to the gate,
the more it turns on.
The more on it is. So like voltage on, more voltage on, and then like more current can flow through. BJT is a current controlled device, which means that the more current I apply to the base, then
through the base.
Base is the equivalent of gate on a MOSFET.
Yes.
Okay, so the more current I apply to the base, the more current can flow through the BJT. Okay, so as far as you are concerned, these are exactly the same thing. Because like the effect is the same. Because you don't like, it's not your problem whether the GPIO needs internally needs to use voltage or current. It's not your problem. Because
it works as a switch.
Yeah.
So you don't care whether which one it works as a switch.
Yeah, we're just telling you because we think it's interesting.
Yeah. I think it's interesting. Okay. Yes.
You want more voltage on the other end, you just shove more power into the gate and then it opens the gate.
You shove a higher voltage. Usually it's VGS, which is gate source voltage. So usually this will be a higher voltage.
Then that will make it
dump more. The resistance of this will be lower if there's more.
Which means more current can flow through.
Yeah. Why do we do this?
Well, this is for information, not why we do this. Yeah. Okay. Yeah. Okay, so yeah, I'll explain that later.
It allows the microcontroller to affect stuff around it. It allows the microcontroller to control its environment.
Yes.
Oh, okay.
Yes. Okay, so a pin, so as explained earlier, it can only pull the output pin low, and so this is why it actually requires a pull-up resistor. like one here. Yeah. So if we just leave this output pin as is, when the transistor is off, this could pick up any stray radio signals and be whatever voltage it desires. So that's why we attach a pull-up resistor here, so that it is fixed to VCC. And when this MOSFET turns on, this will be shorted to ground, and this will be 0 volts. Yeah. Okay, so
did that make sense to everyone? Because we can explain it a different way.
Yeah.
Okay,
yes.
So basically, when the MOSFET is when the switch is turned off, the output pin is not connected to ground, it's not connected to high. So what is it? Don't know, right? So when we don't know what this voltage is, we say that it is floating. So floating basically means I have no idea what this is, and this means that there's an undefined behavior on my GPIO pin, and this means that I don't know what my microcontroller is doing now. So what we do is we add a pull-up or a pull-down resistor whenever we have a floating pin, and this basically like sets the pin to a defined state, high or low. So pull-up means that the resistor goes to high, which means that when floating it will be made high basically, and then pull down just means ground, so that means when floating it will be low.
Because okay.
Yes,
when it's
so
floating, there is always.
Yeah, so when it's floating, it will just like be set to ground.
Yeah.
Basically.
Yeah.
Yeah.
So in this case, instead of a transistor, this is a switch. It's basically the same thing. Yeah, this is the pull up and pull down resistors as we discussed in last lesson. Yeah. Okay, let's move on.
Actually, why do we use open drain, open collector when the other one is more versatile? Like the push and pull.
Oh, he's
Yes.
getting to it.
Yeah, we're getting to it.
It's okay.
We're getting to it. Okay. We'll be explaining the I squared C part.
It does just sound inferior.
If my laptop can respond. Okay. Yeah, so there are different types of GPIO inputs. So now we are sensing data from the real world. And digital input, a traditional digital input, just measures whether a pin is high or low. So 0 or 3.3 volts. And this is read, for example, in Arduino with digital read pin. And there is also a version of like reading analog pins, which basically you're reading a range of voltage instead of 0 or 3.3 volts. So for analog, typically we also must check whether the pin supports analog. Yeah, on some microcontrollers. Can't recall for the ASP whether it supports analog on pins, but I think it should because of the GPIO matrix. Yeah, so okay, yeah. So you can also configure GPIO to act as interrupt pins. So what does this mean? What is an interrupt? An interrupt tells the CPU, or let's say the ESP32, when a voltage goes.
It's exactly what it says on the tin. If a predefined event occurs, it basically tells the CPU, stop whatever you're doing, just drop this service me now.
Yes. So the CPU drops whatever it's doing and just like goes. So it's like emergent.
Program, and then it will just like resume the rest of the program after the thing is completed.
Yeah, I will explain this more in depth later, but like basically it interrupts the current program and it caters to the hardware event first. Yeah, that's it. Okay. So there are two types of, well, there are actually 4 different types of interrupts, but typically we use 2, which is the rising edge or falling edge, because when let's say it goes from low to high, this is an event. Let's say you turn on a switch, then now the microcontroller has to be notified that, oh, you turn on a switch. So this is how you can use an interrupt, for instance, by detecting when the switch turns on or when the switch turns off with the falling edge. Yeah.
Does that make sense?
Okay. So next is analog input. You can wait. Yeah, I did not do this slide. Let's skip it for now. Yeah, basically analog input is just measures a range of voltage. That's all it does.
Okay, so far we have been talking about digital input where it's just low or high.
Yeah.
However, we can also have is ADC and DAC later.
No, we are not talking about ADC and DAC. We can go through that,
Okay,
but I won't have slides for
briefly
that.
I will
Yeah.
explain what it is. Okay, but nobody cares how it works. Okay, so I apply a voltage range. Okay, so I apply any voltage to the pin. Okay, let's say my pin accepts 0 to 3.3 volts, right? Then I apply, I don't know, 2.2 volts to it. Okay, the GPIO pin, through magical means, will tell me, yes, this is 66% voltage. Okay, in reality it will give it to you as like some number between 0 and like a max value.
Yeah, and it's
so it's a proportional thing basically. Okay, so you can
Yeah.
get like more and more resolution in like ADCs or DAC.
Yeah, so
ADC is just analog to digital, DAC is digital to analog. Same thing reversed. Okay,
Yeah.
so like depending on like how nice your microcontroller is, it will give you like a more accurate number.
16-bit, 24-bit, 32-bit. That's the
Yeah.
resolution of the
Yeah.
ADC.
Yeah.
Yeah. Yeah. So
Where's the teensy part? Where's the teensy? I had a slide with the teensy and the GPIO labels.
I hidden it.
Oh.
It should be somewhere in front, but like yeah,
whatever.
Okay.
So basically, GPIOs, they can turn things on and off, but they can also do other jobs. So some of them are able to do analog digital conversion. Some of them are able to do communications, which we'll talk about later.
Yes.
So
but the ESP is special.
Yes. Okay. So for most microcontrollers, like dedicated pins can do certain things. That's it. If you want this function, you have to make sure to wire it to that correct pin.
Yeah.
ESP32, again, through magical means, is able to like dynamically remap its pins. So like basically, it doesn't. There are some exceptions, but basically any pin can do anything. Basically, yeah. So it's in the data sheet. It's called like the IO mux or GPIO matrix. It's not really the same thing, but like nobody cares. And like it's effectively So this is an example of a microcontroller that I like a lot. This is an Arduino. It's an Arduino, but it runs at 600 megahertz. It's like a strong Arduino. Okay, and like it's got a lot of pins. So you notice how like, so these are the pin numbers here. Then these have like A0 to A9. These can do analog. Okay, so this can do analog to digital. Then like there's a bunch of other functions. PWM just means can turn on and off really fast. He'll go over that later. Then like there's the rest of these are basically communications, which we'll also go over later. So like see how dedicated pins have like certain functions. Not a problem for ESP32. That's one of the reasons why we like it so much.
Yeah, so when you're designing boards which you can't remap the pins, then you have to take note of this, especially what are the capabilities of each pin. And usually there are nice graphics that allows you to see at one glance which pin supports what. Yeah. Okay, let's move on. Sorry.
What does it mean by like remapping pins?
Oh, so let's say let's say I've got GPIO 1 to 24, number 1 to 24 on my ESP32. Okay, and I want to connect a communication interface to it. So one of the communication interfaces has two special pins, TX and RX. Okay, it means transmit and receive. Okay, so like in like most microcontrollers, TX and RX are dedicated pins on the board. So like if I want TX and RX, it has to wire to that pin. On ESP32, I don't care. I wire it to like whichever pin is free, and like I tell the software, this pin is TX now, this pin is RX now, and like internally with Magic, it will like connect the chip inside to like the external pin. Yeah, so it can connect its own, it can reconnect its own pins internally. That's what it means.
That's why it's a mux multiplexer. That is actually what it means. Yeah, the name for it in ASP is called GPIO matrix. Yeah, IO mux also.
Yeah, same thing.
Yeah. So different microcontrollers support this differently. Like the STM32 has a different IO mux also, but essentially can do things with certain caveats. So you always must read the caveats. Okay, so that's why it's very important to read the data sheet, but like for now we won't go through that. Okay, skip this. Yes, so this is for your information only. This is how a GPIO looks internally.
This will not affect your life, but we think it's interesting. Okay, don't worry.
Yeah, I think it's interesting, but like realistically you won't really deal with this. And like, but you can see the output stage here. So this controls the output part of the pin. You can see the push pull I mentioned earlier here. And for this is your input, and there's like an analog function and other stuff here. And there's, oh yeah, I forgot to talk about this. You can also configure your pins to have internal pull up or pull down resistors. Yeah, it's magic, you know. So you can just set in your code like, oh, I want pull up here, or you can set your code, I want pull down, or you can just leave it as push pull. Yeah, so that's actually in addition to the input types. Yeah, and of course there's a protection diode, and that's the reason why I cannot connect 5 volts to a pin, because you're shorting this to 5 volts. The diode will die and like bad things will happen. Okay.
Wait, what's the diode for? Is it to connect internal?
ESD diode.
Oh, it's just an ESD?
Yeah.
Wait, so like my logic level is because of the stupid ESD diode?
Yeah.
Isn't it because of all of the internal circuitry?
It's not. It is also because of internal circuitry, but the diode will die first also.
The diode is artificial, so it doesn't like affect the internal circuitry, because like, if you are reading from like higher than the thing, it will fuck up the inside.
Ah, okay.
Ah, yes.
Okay.
Yes, Penny's right. Okay. Yeah, so
again, don't be afraid.
Yeah, don't be scared by this. This is the amount of functions a microcontroller has. And like you can see, there's a bunch of peripherals, there's like security. So a microcontroller can be really, really powerful.
This is another reason why we like ESP32. Very cheap, great features.
Yeah.
So like,
it has Wi-Fi. It has like a bunch of cryptographic algorithms implemented into it.
So this is like hardware optimized circuits. Okay, so like this is faster than like a CPU just thinking about things. Like it will just do the math because the circuit does the math like by magic. So like so it's faster. So it's cool. Dedicated hardware sections for different things is very, very useful. Yeah, which is why all of these are listed.
Why is there RNG?
There's a random number generator. Usually the hardware has to handle that also. Yeah, the hardware is to generate random numbers. Whatever. That's not. It is. Anyways, yeah. Okay, so yeah, CPU, as I explained earlier, is like a brain, and it just gives instructions on what to do and when. Which instructions come one after? Well, not. It's just your brain. Essentially, just think of it as a brain. And there are different examples of CPUs. ESP32 is not really a CPU. There is a processor inside called the Extensa or something, but like this
Extensa
is
LX6.
Yes, Extensa LX6.
It's LX7 now. Sorry.
Yeah, so this is not a CPU by the way, but like yeah, CPUs are the brain of the computer. And memory, yeah, so just like your traditional PC, it also has memory. And there are 3 types. There's SRAM, which is random access memory, which is essentially you can store data that stays there until you reboot the chip. And flash, which stays there. So even if you restart the chip, the ESP32, it stays there. So the flash is ideal for storing code. And read-only memory, that's used internally for the ESP32 for like its proprietary Bluetooth firmware and bootloader stuff. Yeah, but we only care about the RAM and flash, because code is stored in the flash. So whenever you like are in the Arduino IDE, you have to upload code to the microcontroller. Yeah, it's essentially writing code to this flash memory on the microcontroller. Yeah, so okay, so by the way, I'm going to start going into more code, but like this section is just also for your information, and like it's not really necessary in terms of electronics, but I just think it's just fun to teach. Yeah. Okay, so memory is in the microcontroller. As a programmer, you will deal with 3 types of memory, which is mainly the stack, the heap, and static data. Static data is your global variables, and stack variables are essentially the variables you declare in functions. And the heap is managed by the programmer using a special function called malloc. Yeah, so you don't really need to memorize all this, but like, so yeah, stack memory is the most common type of memory. And like, as you can see here, you got two variables, integers and floating point numbers, which are basically real numbers, and they are stored on the stack, and they have, each of them requires 4 bytes, which is essentially 4 bytes of data. And so these 2 variables are stored on the stack, and you can do stuff with these variables, and whenever you call a function, it pushes the function on the stack. Okay, so yeah, and so so stack memory is whenever you have you declare a variable in a function. That's all you need to know. Yeah, and you can also declare arrays here. You can just store them as with values. Yeah, so if actually this piece of code has a bug in it, so how does it have a bug? Well, as you can see, the variables are stored in the function, and when the function returns, the memory is essentially cleared. So that's why we introduce the heap, where we use malloc. And malloc is also managed, it's also part of, like, for example, it's also part of
Hang on, is this making sense? Should you explain how memory in general works first?
Yeah, so memory has 3 components. Like, as you can see here, you got a stack which goes downwards, and you got your heap which goes upwards. Yes.
Imagine a really big Excel table. Okay, a really big Excel table, and I can put like information into each cell of the table. Okay, so I put like some word or some number there. Okay, I need to label that number or word with what information that is. Oh, it's a number. Oh, it's a string. So that's the data type. And then which cell is in the table is it? We call this the memory address, right? So now what he has here with this big rectangle split into smaller rectangles, big Excel table. Okay, big Excel table. You can fill it with as much data as you want, but we organize that data in specific ways.
Yeah.
And like when you fill up the table, you run out of memory, and like
in fact, let's say you got 8 megabytes of flash memory. That's easily 8 million 8 million slots or like rows in the Excel sheet where you can place data inside. And the data is usually a fixed amount. Like, it's, for example, integer, it can go from 0 to 2 million. And yeah, that's a 32-bit number, for instance. Yeah. Yeah, usually we declare variables on stack which are smaller in nature, and on the heap is dynamic, so depends on, let's say you're running a web server, and like, yeah, this is actually out of scope, but like, it's fun to learn. Anyways, yes. Yeah, this is a C programming language which you will work with when you're working microcontrollers. So like, this is just to give you a taste of like what you actually write when you are dealing with microcontrollers as a programmer. Like this is what your programmer is doing. Let's say you're a hardware engineer. This is what your programmer is doing. Yeah.
I have a bit of experience with C#. Is it no?
Not
Mm,
really.
not really the same.
Pointers is still very relevant.
Yeah, so pointers are addresses. So like for instance, the return type of this function is when the function returns, it returns a pointer to this. It returns a pointer to coordinates. Well, like there's an area in memory which has which we allocate 8 bytes in, and yeah, there's an area of memory which stored in the heap, and this coordinates is just a pointer which is stored on a stack. So that's a technical detail, but like yeah, okay, yeah. So static memory is yeah, it's not really faster per se, but like it is stored for the whole duration of the program. So they are just essentially global variables, and they outlive all variables. Yeah. So if you want to learn programming, yeah, this is essentially what you will be dealing with.
I had to understand how static variables work on my previous project.
Yeah. Okay.
It was painful trying to grasp it.
It is. Yeah. Okay.
Yes, it is something
By the way, before I move on,
declared at the start and lives for the entire program.
yeah. Before I move on, is there any questions about like the previous slides? Like this is just for information lah. It's like from the programmer's perspective, what is memory, right? Yeah. Okay. So next is peripherals. So peripherals are everything that is not the CPU or memory. So it's like think sensors, think motors, think like yeah, keyboard and mouse is also considered peripheral. Like yeah, everything that's not the CPU or memory is considered peripheral. And that's why they call it peripheral. It's like yeah,
From
on
east
the outside.
to the side.
Yeah.
Add on,
So peripherals help the CPU by offloading work. So like remember I showed you that big remember I showed you like all the features of the ESP32, most of it, right, except the top left part, it is just most of this are just peripherals. This is peripherals. This also can be considered peripherals if you are really if you stretch the terminology, but like yeah, so everything is interest. Peripherals are where interesting stuff happens in the microcontroller. Yeah. Oh yeah, hardware timers. Essentially hardware timers are also a peripheral, and like it's actually significantly hard to keep time, like to keep track of time in software. So that's why we rely on hardware to keep track of time. And like even though you know like the how much is one clock cycle, in like some CPUs that is actually very hard to determine. So of course you have to measure the amount of time each instruction takes and whatnot. We don't do that. So hardware timers are used, and they are actually quite crucial to when you're using PWM. And PWM, which stands for pulse width modulation, I actually don't have a slide for PWM, but I'll just explain PWM. So what PWM is, right? We use PWM to, let's say, we control the brightness of LEDs. So LEDs can either be on or off, but they can turn on and off really fast to change the brightness. So your eyes will perceive a lower brightness when it's turned off for longer than when it's turned on. So like if you imagine the graph, which looks like this. So the amount of time it is on versus the total amount of time. So this goes on forever. And like this is essentially a PWM signal. And what matters in PWM is the time is on versus the total time, which we usually call T. Yeah, and like, by the way, this is the time axis, and this is your voltage. And so with PWM, what really matters is the duty cycle, which is usually the time on over the total time multiplied by 100%. So this determines how bright the LED is. So if let's say you are on for longer, and this is your repeating waveform, so this repeats, so this will also be longer, for instance, right? It's about the same length, yeah. Sure. So yeah, so now T on is longer, and basically the duty cycle is, let's say now it's 90%, so it's 90% brightness. And the same thing can be done with motors. So the same thing can be done when you're supplying an output voltage to when you are controlling motors. And this is actually how you change the speed of motors and how you change the brightness of LEDs. Yeah. And servos is a bit different. Servos, the angle depends on the duty cycle, if I remember correctly. But the for servos, you have to take note of the frequency of the data.
Okay.
Yeah.
For those who do not know, a servo is a motor, and the motor will set itself to a specific angle
based on this waveform.
Okay. So
yeah.
An LED is just a dumb, it just turn on and off. Okay.
Yeah.
And your eyes are doing like the dimming or not. It's tricking your brain.
It's tricking your brain. Yeah.
A servo is it's a motor with a magic box between like the microcontroller and the motor. Okay.
Yeah.
The based on the duty cycle, it will map that duty cycle to an angle. So for example, the motor can go from 0 to 180, and it accepts a duty cycle from 40 to 70%. Random numbers are pulled out of thin air.
Yeah.
So depending on how far along you are from 40 to 70%, it will determine what the angle will be, how far along you are from 0 to 180.
Yeah.
Okay. So it's a linear mapping usually of duty cycle range to angle range.
If you want more in-depth explanation, you can ask me later.
Yeah. So yeah, this essentially is what we use, and actually, in fact, most lights are PWM because of 60 hertz. Like if you actually like record lighting, it will flicker. That's why. It's to save energy also. Yeah. Okay. So next we'll be talking about inter-chip communication. And like this is when you want to communicate with sensors. And pretty much we'll be covering UART, which is serial, I2C, and SPI. And those are the three most common protocols. Yeah, so UART is actually the simplest communication protocol out of the three. What it does, it has 2 pins, so transmit and receive, and it uses 1 pin. So let's take a look at the transmit pin. It uses a single wire and it just transmits data, and so it looks like this actually.
What the hell is that?
Yeah, I mean, what that is
two waveforms on top of each other.
Yeah, but it could be either high or low. So yeah, so this is like one data line of UART, and basically this is the data bits, like from 0 to 8. So you are sending a byte over. A byte is 8 bits, by the way. And with UART, there's always a start bit, and you got 8 bits, 8 data bits. Optionally, you can have you always have a parity bit and a stop bit and an additional optional stop bit. So essentially it's just sending data over 1 pin. That's all you need to know. And there are and it can go in two ways. So you got essentially when you're wiring up UART, the most important thing to take note is yes, draw diagram. Yes. So let's say this is your ESP32. It has GPIO pins that you declare to be transmit and receive, right? And then this is your sensor, which also has TX and RX. So TX stands for transmit and RX stands for receive. And so typically what you do when you wire things up is you have to cross them like this. Why you do this is because from the sensor's perspective, it is receiving data when the ESP32 is transmitting data. So you will have the data coming in over here, like whatever data it has, and you'll receive over here. And the same thing goes in this direction. So in fact, the data flows like this, and the data flows like this. So that's why we call this bidirectional with two pins. Yeah. And this is also why UART is called serial, because data comes in sequence. Yeah, and that's what serial means.
I mean, the reason it's called serial is because originally it's parallel. They just it's
yeah,
not transmitting one
parallel
at a time. It's transmitting all at once, like the entire bus width.
Yeah, so
But that's really expensive in terms of like space.
so
and
let's say this is a
cost and
byte,
stuff.
right? So there are 8 data lines. So a parallel port can have 8 data lines, and that transmit one whole byte at once. So like that could mean like it's transmitting a number, for instance. But like this one, when it's transmitting a number like from 0 to 256, which is what can fit in a byte, what can fit in 8 bits.
255.
Yeah, sorry, 255 minor 1 off by 1, but like it transmitted in an amount of time. Well, this just transmitted in one shot. That's why this is a parallel port, this is 0. But there is additional information. Yes. Parallel ports are very old technology, and like
I mean, we still like it for like screens and things, you know, because it's like
yeah. I mean, like
this is a side note, okay, but like so serial just means one after the other on the same line.
yes, one after
Parallel
the
means actually more lines, right? And like imagine I have 24-bit color on my RGB value for each pixel of my screen, 10,000 pixels on my screen, you know, and then like each one has to have 24 bits, then 8 bits for RG, and it will take me forever to send all that data using like one line. No problem, my friend. I have 24. I send you the entire pixel data at once. You know, so like parallel is great for like stupid high data rates, but we don't really use it for like most things because the other stuff is usually good enough.
yeah, like when you can go out to gigabits with just USB, and USB just uses one data line, but two, but
Three.
differential.
Where's the tree ground?
Hmm?
What's the
Like
third?
for which are you
Data
referring to?
There's
There's at
USB2.
least 5 versions can be referring to right now.
Yes, USB2 usually we
No, just 480 megabits per second.
yeah, okay. Yes, USB 3.0 is different, but yes,
Which
we
is 3.0.
okay, yes, we don't talk about that. Okay, anyways, yeah, so with UART, there's actually parameters which we have to set on both the host and the device. So with UART, we have to set the baud rate, which is essentially
Basically just how many symbols it sends per second.
yeah, so like using the baud rate, you can figure out how long is a UART data frame. Like this. Like the time taken, I should draw. Like okay, so normally it's I, then you got the start bit here, Then you got your data bits here. So your data bits can be anything. So usually we denote them like this. Then you got your parity bit. Then you got your stop bit, which I believe it's a high. Yes. Then this is your next frame. So this is one frame. So this is your stop bit, and this is your start bit. And this start bit is essentially to tell the microcontroller or the device that I'm transmitting a frame. And the time taken for one frame is determined by the baud rate or bit rate. Yes. And the baud rate or bit rate is usually set to a nice number, or like standard numbers, not nice, but like, yeah, it's usually set to 9600 usually, or 115K. Yeah.
Is that like when I use the ESP, I remember typing in something and then 115200.
Yeah. So usually you got your baud rate, which is like 9600. Then you will see this notation regularly. You got comma, and you got n, and you got 1. So this is your baud rate. This is your parity bit. So this is your parity for a label. So and this is your stop bit. So there can be one stop bit or two stop bit depending on this number. So this is 1 or 2. This is parity or no parity, if I remember. So n means no parity, so this can be missing also. Yeah, but essentially your baud rate measures this, and your actual data rate is this. So take note, like with for example this, usually we don't have a parity bit, so like this is missing, and this, and so your efficiency of the message would be 10 bits, right? So so your bit rate will actually be 960 bytes. How I come up with this number is because this is the baud rate, and there are 10 bits in this. So by dividing by we divide by 10, multiply by 8. Yeah, so just always know that the bit rate it is smaller than the baud rate. Yeah. Okay. Yeah. Okay, next is I squared C. I squared C is, unlike UART, has 2 pins. It still has 2 pins. But wait, yes, it has 2 pins. One for bidirectional data and one for clock. So unlike UART, which relies on which relies on the clock of the receiver and of the host and device, I squared C has a clock and data line. So essentially what it looks like is, so when wiring I squared C, you would have ESP here, and you would have serial clock and data, which usually is labeled by SDO. Wait. SDA, yes. SDA. So this data, this clock, and your clock would always connect to your device like this. So it's actually quite simple to wire up. So SCL and SDA. And so the clock would is a regular, it turns on and off, and it synchronizes the data. So the clock is the reason why you do not need to provide a baud rate for I2C.
Every time clock goes high, everyone is like, oh, data is coming.
Data is ready when
okay.
clock is
Yeah.
when the clock goes high or goes low depending on the implementation, but that's we don't care about that. Yeah. And the data is determined by the clock. So like and with I2C, there's also you can connect multiple devices in parallel. So you can connect like from this to this, this to this, and it's the same pins. So you actually can connect up to 128 devices in all in parallel using the same I2C bus. Okay, so this is what we call an I2C bus. These two lines are called a bus, and we can wire up to I believe 128 devices.
27.
127, 128.
27.
0 is reserved, I think. But yes, because 7 bits is okay. I'll show you the protocol.
Something is reserved. I don't know. I just remember there's a -1.
Yeah. Okay. Yes.
Anyway,
So
you're
that's
never gonna put 127 devices on one bus. Like, try and do that. Yeah.
I mean, you might have.
Okay, so remember, because every single data has an address, each device has a different address.
Yes.
And the address is not something that you can just change whenever you want. A lot of the chips will have just some address, and like you just deal with it. Okay. So like sometimes you cannot use a chip because it has an address which conflicts with like another address.
Yeah. So
You know,
the device
It's quite rare because there are enough addresses to be clear. But like it means that you cannot. It's difficult to totally fill the bus with all the devices. Yeah.
So let's say since the address is baked to the device, so since the address is baked to the device, sometimes if you use two of the same type of device, so let's say this is a barometer sensor which measures pressure, by the way, and the barometer has address, let's say 76, hard coded into its device. When you use the same barometer on the board, it has the same device, it has the same address also. So it will conflict and it will respond both at the same time because it thinks it is talking, the device thinks the ESP is talking to me, but they both have the same address. So like they both would respond back and bad things will happen. Yeah. So on some devices, they would have other pins to configure the device. So like maybe you have a address, let's call a random pin. Then you pull this to 3.3 volts. So this address pin of the device is 3.3 volts. Then because usually you should add a resistor here, but like if you put this to high, then the address will change for the device, and you put it low, the address will be 76, for instance. So this way, some devices with multiple address pins, so there can be multiple address pins. So you can configure depending on whether you pull it up or pull it down. You can configure multiple devices of the same type on the bus. Usually, the more address pins you have, the more devices of the same type you can use. Yeah.
How does the microcontroller send the address?
Yeah. So that's what I'm going through next. Okay, so I don't know. So
The diagram is getting worse. I think terrible.
okay, so yeah, so
To be clear, right? I don't know any of this timing diagrams. I understand all the words, okay, but like the diagrams could not tell you.
Yeah, I mean,
I know what the common speeds are. That's it. So like
when you're,
yeah.
I guess this matters more when you're doing software, and like when you want to try to debug like what the hell has gone wrong with your chip.
Oh yeah.
Yeah.
Like you will put an oscilloscope there, and you
Yeah.
will look at the waveforms,
You
and you'll
actually
be like, "Where's my clock signal? Why is it missing?" Yeah, but
Yeah.
just don't be in that situation. No problem. Sorry.
yeah. So as you can see, the slave address, there's 7 bits that's transmitted here, and for each bit is synchronized by this vising.
Wait, where are the bits? It's all just ones, isn't it?
This one?
Dumb.
No, these are either 1 or 0.
I can't see what's going on.
I think it just means
Okay, never mind. Nobody cares about the waveform. Talk about like how it's split up and that's it.
Yeah,
That's
so
fine,
there's the
right?
slave address here. There's a read write bit depending on whether data is flowing to the microcontroller or from the microcontroller.
Yeah. So
Yes.
the address is always 7 bits. Okay. Then the last bit of 7 bits plus 1 extra bit. The last bit is purely read or write. So the last bit will tell you, oh, am I reading or writing right now? That's what matters.
Yeah. And the data, the data is usually configured like 8 bits, or some microcontrollers, no, so some devices will specify the amount of bits of the data. And like sometimes you can, I believe, yeah, the microcontroller will specify the number of bits of data. So this one you have to read the data sheet of the device, and it will tell you. Yeah, this is also for your information. Yeah, so for I2C lines, you actually, I forgot, there's something missing in this diagram. You actually have to put a pull-up resistor. So you have to put a pull-up resistor. Why? So you have to put like 2 resistors here, and they are connected to VDD 3.3 volts. Why do you have to do this? It's because I2C, by nature of its one master, multiple slaves architecture, so slaves and devices are interchangeable, and master is usually the ESP. And because of this nature, it has open collector outputs. So that means the ESP has an open collector output on this, and the device also has open collector output or input depending on whether it's receiving or sending. So what this means is that multiple devices can be put on the bus, because everything is connected on the same bus, and each device can only pull this line low. And so with the pull-up resistors, because every device has an open collector output, which I mentioned that term earlier, high impedance, which means that this whole bus is left floating if you do not put these pull-up resistors, which actually set the voltage to 3.3 volts normally, right? So when, let's say so I forgot to tell you that like this part of the diagram is initiated by the host, always. The host is the ESP, and the ESP is doing the pulling down. So the ESP is switching a transistor on this line. So you can imagine a transistor here. It's switching a transistor on this line. And so that is where this slave address comes from. And the ESP tells whether it's read or write. If it's read, now the device has to send data over. So let's say the ESP sends 1, which I think stands for read. I'm not sure which is which, but it doesn't really matter. Let's say the ESP sends a read command like here, and it sends the address. Now the device responds with a acknowledge. So it will respond with whether I acknowledge or I do not acknowledge. So, and then it sends the data over. So how does the slave pull this line down? It also has its own transistor, and once it receives from the bus, it will also pull the bus low right here. So that means the ESP has to stop transmitting or leave this transistor off. Then it starts sensing the input. Yeah.
Doesn't the pull-up resistor just flood all of the wires with like 3.3 volts?
Yeah, that's the whole point.
Oh, but then how do you send the signal at all if it's flooded?
Because this is just a resistor. So let's say this is 10K.
10K ohms.
Ohm.
Big value. Relatively big value.
So when the transistor is turned on, this would say maybe it's like 2.7 ohms. So this will be put down to ground.
It's more like 30 milliohms. Basically zero. Basically zero. It's so small that nobody cares. So then you form a voltage divider between 3.3 volts, the 10K resistor, the MOSFET resistance, and ground. Because the MOSFET resistance is so tiny, it's basically zero. The line is basically 3.3 volts.
The line
Is that correct?
Well, the line is basically 0 volts.
Yeah, basically zero. My bad. Yeah.
But then, wouldn't that ground everything after it also? Like you look at the device.
Yeah, everything will be ground. This whole bus will be ground.
Oh.
And that's the beauty of open collector, because if let's say the device is misconfigured and this guy also pulls it down, so two devices are writing to the bus at the same time. That doesn't matter. Okay, let's say this device also pulls it to ground through the transistor, and it doesn't matter because both of them are ground and like nothing bad will happen.
But if it's push-pull, then what if one is push and one is pull? Then you have a short from VDD to ground, and then like much current will flow and everything will burn, So like this is why we use open drain and open collector. It's not better for like normal things, but when you have multiple things connected to the same bus, suddenly it's very safe, because nothing can burn because you only rely on the pull-ups to make it like high, and that's it, and the pull-up is big enough that it limits the current going through the MOSFET, so the MOSFET cannot burn.
Yeah, so that's why SQSC is quite special in that it only use one pin for bidirectional communication. So either the host is talking or the device is talking. If both are talking, then like no,
the data won't make sense, but
The
at least nothing will break, Yeah.
nothing will break, and that's usually a I2C conflict or I2C bus conflict. We usually call it that. Yeah, but like you might run into this problem